Hi, this is Sasha Welch. Today we're going to be talking about continuity, which is section 2.5 in calculus. First, we're going to talk about the formal definition of continuity. If C is a real number that is either an interior number or an endpoint of an interval in the domain of f, then the function f is continuous at C if the limit as x approaches c of f of x equals f of c. So let's talk for a second about what that really means. If we have a function and there's some interval on that function and c is in that or it's an endpoint of that interval, then we say that f is continuous at point c if the limit at x is c is the same as the y value at c. So the two sides are converging at that point C, and also the y value is point C. To go along with that, we can say the function is right continuous at C. Sometimes we say it's continuous from the right if the limit as x approaches C from the right or from the positives of f of x equals f of C. So this is kind of like half of the actual definition up here of continuous at C. We say that it's right continuous if I'm approaching it from the positives, from the right side, and the function itself has that y value at C, then it's continuous from the right. And the opposite of that, we can say the function is left continuous at C, or it's continuous from the left if the limit as x approaches c from the left or from the negatives of f of x equals f of c. So the same thing we've been saying, except this time we're coming at it from the left. If my limit as I'm approaching x from the left, as I'm approaching my c value from the left, is the same as the y value of that c. So if we look at a little picture here, we have our interval from A to B, and C is right there in the middle. So that's our first thing we're saying. C is some number that's in that interval of A to B. Then we can say the function is continuous at C right here if the limit as we approach C from both directions is the same as the y value there at C. We could say over here at A, I have continuity from the right because as I come at this point A from the right, it's the same as my y value at A. And we could say at B over here, as I come at this value B from the left, it's the same as my y value there at B. So that's what all of those different things are saying. C is the only one that's actually fully continuous because it's coming from both the left and the right, and it has a y value there at C. So as we move on, we have what we call a continuity test. We say a function f of x is continuous at the point x equals c if and only if it meets three criterion. 1, f of c exists. The y value at c actually is there. 2, the limit as x approaches c of f of x exists. So not only does a y value exist there, but there also exists a limit. And last but not least, those two things are the same. Your limit as x approaches c and f of c are the same value. So in this graph over here, you can see that the whole red part is continuous until we get to 2 pi. And then this whole green part is continuous until we get to 4 pi. But here at 2 pi, our graph is discontinuous. It is not continuous. I have a left-handed limit coming up at 2 pi of 0. I have a right-handed limit coming up on 2 pi at about -3. However, 0 does not equal -3. So since those two things are not the same, this is not a continuous function at 2 pi. We have different types of continuity and discontinuity. Continuous graphs are just continuous. That's pretty much all there is to it. And a discontinuous graph could just have like a little hole in it. We call that removable discontinuity. It's like we've just removed a part of the graph. Sometimes it might have a point on that same x value, but if it's not right there continuous, we call that removable discontinuity. Sometimes my graph has a different piece above or below it. We call that jump discontinuity. It's like the graph jumps up or down. We could have infinite discontinuity, where my graph is approaching infinity, maybe even positive infinity from two directions, but that doesn't mean it's continuous. It doesn't connect up there at infinity. And we have a really nice example of oscillating discontinuity. I'm oscillating between -1 and 1. It's not really approaching either one. I can't choose one exact number that this graph is approaching, so we call that oscillating discontinuity. I have 3 examples that you can try on your own. If you're watching this, it probably means that you're gone, and so you're catching up. So if you want to pause the video right here and try these, you can. Keep in mind that denominators of fractions can't equal 0, and even roots can't be negative. That's going to help you determine where these are continuous or not. And the next slide will have your answers. So if you need to pause it now to check, go ahead. And check your answers. Letter A is discontinuous when x equals -2. So you set your denominator equal to 0, x is -2. So you're continuous except at x equals -2. Letter B doesn't have any fractions or square roots. It's continuous everywhere. And letter C, we're going to set 3x minus 4 less than 0. X is less than 3/4. That's where it's discontinuous. So it's continuous from 3/4 to infinity, and 3/4 gets a bracket because it can equal 3/4. Let me know if you have any questions. Shoot me an email. Thank you so much for watching.